something. So there's two kinds of math classes, right? There's a kind of math class where you study things you already know about, but you study like specific things about it, which is sort of like this chapter. And then there's a kind of math class like, if you're taking abstract algebra, I'm gonna introduce you to this new object and we're gonna study it all semester. And like groups, you're like, what the hell is a group? And then you learn what a group is and you learn all these things about it. Well, tomorrow's starting like with chapter 2, well, only chapter 2, but chapter 2 sort of like that. It's gonna be like, here's a bunch of words you've never thought about or heard about, let's learn about them. So it'll be a very different feel. So there won't be inequalities like this for at least another week and a half. So you guys will just instead be next week is gonna be a vocabulary class. It's going to be like compact set. You're going to learn words like compact. You're going to learn stuff like connected. You're going to learn all these words you haven't thought about before, but in a mathematical way. So it'll be cool. So then if these inequalities are getting to you now, there's a little break coming. So for them to absorb into your brain. Great. So we're going to talk about the complex field, but I'm going to present it like Rudin does. And now I'm convinced that this is a good way to present it, at least in the context of this course. So consider R2. Actually, we're not going to start this with a definition. Let's start with R2. With the regular addition. And define, it's probably capital D, for two elements of R2. So these guys are both in R2. Define this multiplication. I always get this wrong. We'll look together. AD plus BC. All right. If we define this multiplication, we have the following theorem. R2, the usual addition and the above multiplication is a field. So if I take R2, we already kind of know what R2 is, and I give this kind of weird way to multiply vectors, I get a field. So again, this is where I was going to ask you guys, do you want me to prove it's a field? I know I haven't done it for anything. I'd be glad to at least go through some of the axioms to prove it's a field. Does that seem reasonable? Sure, so let's prove, so there's 9 axioms. I'm not convinced we need to go through all of them, but if you guys want, we can go through all of them. But let's do at least the addition ones, maybe distributive ones, just to show off how they work. The only reason I'm doing this is because, I haven't done a proof of anything being a field, so it'd be nice to see one. So A1 tells us that if I take 2 things and add them, actually let's not do A, let's do the multiplication ones. And the reason we want to do the multiplication ones is we already know the addition ones all work, right? Because because it was already a vector space. So let's just prove the multiplication ones. Does that make sense? So first multiplication one tells me, so this says one, so we want to show if x and y are in R2, then x dot y is in R2. Right? Let's just do it. So let xy be in R2. So let's say with x equal to a comma b and y equal to c comma d. I'm not actually going to go through with it, but x times y is just equal to, as I wrote over there, ac minus bd. And AD plus BC. And it's clear, because the reals are a field, this is a real number, this is a real number, so this is an R2. Great. So multiplication 2, this would be the commutative property. So this is, we want to show again, x dot y equals y dot x. And I've already written what x dot y is up there, so let's just get what y dot x is. Well, this is just equal to CA minus DB, comma, dA plus C, right? If I'm keeping everything in order how I defined it. And I mean, that's obviously the same. But these two are obviously equal. Yeah? So good, multiplication 2 is, it's commutative. Associative. I'll just go through multiplication, maybe distributive property. But okay, M3, so it's associativity. So now we now have to show if X, Y, and Z are in R2. Then X, we have to calculate the following two things. X dot Y dot Z. I should give everybody names. CD. So this is just equal to AD minus BC, AC plus BD dot EF. This is why nobody likes to do this, by the way. ADE minus BCE minus ACF plus, so this is just the minus minus, BDF, comma, now I have to do the other guy. Yeah, is that right? Did I mess up? I'm pretty sure I messed up, but I don't know where.
AC minus BD.
This times this guy minus this times this guy.
Well, in the first line, it should be AC minus BD.
Oh, this one? Yeah, you're right. Well, that sucks. So that means the C and the D were changed. Yeah, there we go, problem solved. Probably over here too.
The second term is 1 2 now.
What'd you say?
The second term is AD plus BC.
Second term is AC plus B.
AD.
Yeah, I don't know what I'm doing. Yeah, that's what happens when you try to do everything on the fly and off the top of your head. AD plus BC, yeah. So now we fix that over here. AC, AD, BC, AD, BC. See, problem solved, it was easy to fix. But the point is great. I mean, this is kind of boring, right? Now I'd have to actually do this one. I mean, can you guys just believe me it'll be the same? I mean, you compute this other horrible thing and it works out to be the same thing. I'm just sorry, I just don't like, I'm bad at arithmetic. You'd be surprised, I'm so bad at arithmetic. And when it comes to these symbols, I do stuff like that and I just don't pay attention and forget I was not paying attention. But okay, I'm glad you guys caught it. I mean, I really should have a shirt that says, I don't make mistakes, I just check your awareness or something like that. Whatever. But this, I do, I mean, trust me, my advisor is like it's like a world-renowned analyst. And whenever you sit in a class with him, at least like once every 30 minutes, you make some like glaring, like basic mistake. It's just how analysis works. You're doing so many of these things, you make these mistakes. That's why you have to check your work on your homework. But fine, you get this, and then we have like, this comes out to be the same thing. M4 is the one where we, oh, right, we should do M4 and M5. Because this one's less obvious. So M4 says, so I want to show there exists something in my R2 such that this times any x is equal to x, right? So this one's actually an interesting one, unlike the first three, which are just compute a bunch of crap, right? What I have to do is I have to tell you what's going to work like my identity. I know I erased the definition, but could anybody tell me what the identity is probably going to be?
0, 1.
It's going to be 1, 0. So if you look at 1, 0 multiplied by any AC, you see that this is just, well, this is AB, sorry. This is just going to be A, and this is just going to be B. Yeah, because if you notice, all the cross terms occurred from having something here. Okay, cool. So yeah, 1, 0 is my identity. So 1, 0 is the identity that I'm looking for. Maybe I'll give this an extra line. So you can tell the difference between the 1 and then the 1, 0. Great. And then M5, this is even harder. So I want to show x not equal to 0, x, let's say AB, is AB. There exists some 1 over x in my set.